Hello everyone and welcome once again to series of carbohydrate lecture. This time I'll be talking about stereochemistry. And stereochemistry is very much important in the study of carbohydrates because we will be seeing how the molecules are, particularly the carbohydrates or the monosaccharides, are arranged, or the atoms in monosaccharides are arranged in space. That's why stereochemistry is a science that is concerned with the study of how atoms are arranged in space. So, um, be with me in the study of this topic, and let's move forward. Um, Let me share with you first some terms that we will encounter. Chirality is a study wherein we take a look at the handedness in molecule. And handedness is a form of isomerism. When we say isomers, remember they are compounds or same molecules, but different arrangement of atoms. They have the same molecular formula, same number of atoms, but different arrangement of atoms and space. So those isomers, though they have the same molecular formula, but they differ in arrangement, they are different molecules. Okay? Most monosaccharides exist in two forms, a left-handed or a right-handed one. So for example, you have a left hand and the right hand. Um, the relationship between your right hand and your left hand is what we call mirror image. So if you have your right hand, and if you face the mirror and look at your right hand, what appears in the mirror is your left side. So let's have a picture here. So the relationship between left and right is called mirror image. Right? So the right hand is the mirror image of left, and the left is the mirror image of the right. Mirror image is the reflection of an object in the mirror. Okay? So now, another term is called superimposable. Superimposable mirror images. These are molecules in which when you these are the molecules or images that coincide at all points when are when the images are laid upon each other. Say for example, you have a molecule here, okay? A carbon, this is a propyl bromide, okay? Propyl bromide or bromopropane, okay? So the first carbon has bromine, and it has, of course, two hydrogen atoms. Okay, and then when this molecule is placed in front of a mirror, what appears is this. Okay, so what appears in the mirror is actually the mirror image of this molecule. Okay, now this molecule, the propyl bromide or propyl bromide, is known to be superimposable mirror image because when you when this molecule, okay, when when the mirror image, okay, when the mirror image of this molecule is placed on top of the other, when this molecule is placed, okay, or laid upon each other, all points, it says here, all points coincide. Okay? So, for example, when you lay this mirror image molecule on top of this, all points coincide. What does that mean? So when you put this upon on top of this, the Br will be here also. The two carbons will be here also. Okay. Okay, the CH3, CH2OH will be on top of this group also. And the hydrogens, the hydrogen atoms will be on top of these hydrogens also. This hydrogen will be above this hydrogen, and this hydrogen will also be above this hydrogen. So it says here, all points, okay, coincide when the images are laid upon each other. That's why they are called superimposable. Okay? Now let's proceed to another type of molecules. They are called non-superimposable. Okay. It says here that non-superimposable mirror images are molecules or images where not all points coincide when images are laid upon each other. Now notice that in this representation, you have a black circle, and bonded to it are four um, different colored circles. Let's assume that this molecule, um, the black ball, represents carbon. Remember, we have we know that carbon is capable of forming four bonds. Okay, so each of this represents different atoms. Let's say this is the yellow is hydrogen, the green is for um, let's say fluorine, okay, and then this is for chlorine, and this is, for example, iodine. Okay, now when you place this molecule, okay, in front of the mirror, what appears is this. So this is the mirror. This is the mirror image of this one. Okay, so what you see in the mirror is like this. The chlorine will be towards you. Okay, and then the fluorine atom will also be something like towards you also. This one, something like it, the orange ball goes a little backward. Okay, now when you when you put or when you laid this molecule, okay, bring this on top of the other, okay, without rotating, okay, without rotating, um, what will happen is the images or the points will not coincide. Okay, so bring this to bring this molecule on top of this, then not all points will coincide. Okay, the yellow will be somewhere above the chlorine, above the orange here. Okay, the orange here will appear above the yellow. Okay, yellow atom here. So that's what super or non-superimposable mirror images behave. Okay, so not all points coincide. The reason why non-superimposable mirror images behave like that, because it has what we call a chiral center. Okay, it has a chiral center, and we will see what it means by chiral center in the coming slides. So you have to remember that a superimposable, okay, the chiral center is banded to the different banded to four different groups. of atoms. Okay? In our example earlier, in the molecule that is superimposable, remember the CH2 or CH3, then you have here CH2, and then carbon, Br, okay, and there are 2 hydrogen atoms. Okay? This molecule, the propyl bromide, does not have a chiral center. Okay? So that's how the superimposable and non-superimposable differ. This one, as we have said earlier, this is superimposable. All points coincide. Okay? One of the reasons is it has no chiral center. Okay? A chiral center is an atom that is connected to 4 different groups. So if we examine this atom, how many groups of atoms, different groups of atom are bonded? So this is one group, another group, and then there are 2 hydrogens, so they are the same. So we count how many groups? Different groups, 1, 2, and 3. Okay? Whereas, in this molecule, in the superimposable, it has a chiral center. It has 4 different groups. 1, 2, 3, and 4. Okay? Now, as you can see here, this is a molecule that is, does it have a chiral center? Yes, denoted by an asterisk. So let's say this is the carbon connected to chlorine, fluorine, hydrogen, and bromine. Okay? If you place this on top of the other, okay, even with rotation, it cannot be superimposed. Okay, not all points will coincide. Unlike this one, okay, dichlorofluoromethane. This is carbon with 2 chlorine. That's why it's dichloro with fluorine, dichlorofluoromethane. So what happens is if you put this, if you lay this mirror image on top of the other, not all points or all points will coincide. So it says here can be superimposed. Okay? Talking about chirality, I said earlier, a chiral center is an atom in a molecule that has 4 different groups. Okay? Tetrahedrally bonded to it. So a chiral center is an atom that must have 4 different groups. And a molecule that contains chiral center is said to be chiral. Okay? So take note that a chiral center is an atom that has 4 different groups. And if a molecule that has a chiral center is said to be chiral. A chiral molecule is a molecule whose mirror images are not superimposable. Okay? And achiral, or let's say not chiral, is a molecule whose mirror images are superimposable. Achiral meaning not chiral. Okay? That means when we say achiral, it has no chiral center. So I have here examples of molecules with chiral center denoted by asterisk. So butan-2-ol or 2-butanol, okay, it has a chiral center, the carbon atom number 2. Okay? it has 4 different groups. So let's say this is one group 1, group 2, group 3, and group 4. They are different. Okay? So it has a chiral center, therefore this molecule is chiral. The mirror image, the mirror image of this, the mirror images of this molecule are what? Uh, Non-superimposable. Okay? Now, as I said, we can apply this principle to monosaccharides because monosaccharides, or the sugar units, okay, when you say monosaccharide, one sugar unit, okay, some of them are, or many of them have chiral centers, therefore, they are chiral molecule. Okay, so right here, we have um, glyceraldehyde. Okay, glyceraldehyde is the simplest monosaccharide. Okay, so the first carbon, this is the aldehyde group. Remember, this is the aldehyde group. And then on the second carbon, there's an alcohol. Okay, on third carbon, there's also alcohol. But notice that the second carbon is chiral. Let's put asterisk. Okay, the first carbon is not a chiral center. The third carbon is not a chiral center because there are 2 hydrogens here. Remember, 2 hydrogens is equivalent only to 1 group. Okay? So here, there are only 3 groups. In carbon number 1, there are also 3 groups, but in carbon 4, there are 4 different groups. That's why um, the mirror images are non-superimposable. Dihydroxyacetone is what? Achiral. Achiral meaning not chiral because it has no chiral center. Number 1, there are 2 hydrogens here, so there are only 3 groups of atoms. Okay? In carbon number 2, there are only 3 because this is considered as one group, another group, and oxygen. So chiral center is absent in dihydroxyacetone. So if it has no chiral center, then the molecule has no mirror image. Okay? Stereoisomers are isomers that have the same molecular formula, same molecular and structural formula, but differ in the orientation of atoms in space. So that's what we are talking about. Okay, we are working on molecules that have the same molecular and structural formula, but different orientation of atoms in space. There are 2 types of stereoisomers. What is called enantiomers, and the other one is diastereomers. Enantiomers are stereoisomers whose molecules are non-superimposable. Okay, remember, always think of it that when we say non-superimposable mirror images, the molecules, when the mirror images are laid on top of the other, not all points coincide. So the left and right molecules, the left and right-handed form of molecules with a single chiral center are enantiomer. So even though the molecule has only one chiral center, then it has a pair of enantiomer. Okay? Even the molecule has only one chiral center, it has a mirror image. It has a pair of enantiomers. Okay? So for example, we have here D-glucose. Okay? D-glucose. In D-glucose, this is the Fisher projection. When we say Fisher projection, the the chain or the glucose molecule is in two-dimensional, okay, open chain. So this is the carbon being number 1, carbon 2, 3, 4, 5, 6. Remember in this presentation, in this structure, we are using line formula. Okay? In organic chemistry, we can use a line formula to denote carbon. So this section here, okay, for example, you have like this. Okay? This is equivalent to a carbon, another carbon, and another carbon, and another carbon. So you have 4 carbons here. Okay, 4 carbons. This is similar to this. So, but here we are not writing those carbons anymore. Simply lines. On the second carbon, the OH is at the left. Okay, on the third carbon, on the second carbon, the OH is at the right. On third, on the left. Fourth and fifth are on the um, right side of the plane. Let's consider this as a plane. Okay? So this is D-glucose. D-glucose has chiral centers. It has chiral centers. Okay? How many chiral centers are there? Actually, it has 4 chiral centers. Carbon number 2, carbon 3, carbon 4, and carbon 5 are all chiral centers. What's the definition of chiral center? They must have 4 different groups. Carbon number 1 is not a chiral center. Carbon number 6 is not chiral center because remember, there are 2 hydrogens here. Therefore, there are only 3 groups. Okay? In carbon number 6 and carbon number 1. Okay, so it says earlier that even though there's only one chiral center, then the molecule has a mirror image. Okay, so here in this molecule, in the D-glucose, there are 4 chiral center. That's why it has a pair of enantiomer. It has a mirror image. So what is the mirror image of the D-glucose? It's L-glucose. Okay? L-glucose. So notice the orientation of the atoms. Okay? In the D-glucose, the OH is at the right. In the L, it's on the left side of the plane. Okay? And then here, from left, in the D, it's now on the right side. On carbon number 4 and carbon 5, the OH are at the right side, now on the left side. Okay? The carbon atoms, the atoms in carbon number 6 does not change because remember, this is not a chiral center. Also, the atoms in carbon number 1 do not change because this carbon is not a chiral center. So, an L is a mirror image of the D. Okay? I repeat, L is a mirror image of D. Okay? L and D, they are what we call enantiomers or pair. Okay? Pair of enantiomer. Left and right-handed. The D enantiomer is right-handed. Okay? The L is left-handed. All right. Now, how do you know? How do you know whether the molecule is D or L? Okay? That's the question. How do we know whether the molecule is D or L? Now let me draw another structure here. So let's say that we have a 4-carbon monosaccharide. All right. This is uh, a 4-carbon monosaccharide. We said it's called tet tetrose. Okay? Tetrose stands for 4-carbon atom, aldose. This is the carbon number 1 is the aldehyde, aldose. Aldotetrose. Notice the orientation of the atoms or the OH. Okay? On carbon number 1, this is not chiral center because there are only 3 groups. Okay, carbon number 2, is this chiral? Yes, this is chiral because there are 4 groups. Okay, the aldehyde group above, the OH at the right, the hydrogen on the left, and then the group at the bottom. Okay, so in this molecule, um, aldotetrose, it has 2 chiral centers. The 4th carbon is not chiral once again because there are 2 hydrogens here. They are considered as one group, so there are only 3 groups, different groups bonded to this carbon atom. Okay, so take note, in aldotetrose there are 2 there are 2 chiral centers, the 2nd and the 3rd carbon. Now the main question earlier is, what or how do we know whether the molecule is D or L? Okay? D or L. There are hydroxyl group. There are OH here at the right. There are OH here at the left. Okay? Now, to know whether the molecule is D or L, you will identify the chiral center farthest from the aldehyde group or farthest from the functional group. I repeat, you will locate or identify the chiral center that is farthest from the aldehyde, or you will identify the highest numbered chiral center. So, carbon number 2 is chiral, but carbon number 3 is also chiral. Okay? So, the carbon number 3 is the highest numbered chiral carbon. Carbon number 3 is farthest from the aldehyde. Now, after you have identified the chiral center farthest or highest numbered chiral center, where is the OH, where is the hydroxyl group? If it points to the left, then that is an L. Okay? However, if the OH on the highest numbered chiral carbon is at the right, then you have a D. Okay? To further explain it, let me draw another molecule. Okay? And let's put the aldehyde group there. OH here. All right? And another OH. Okay? This time I have here OH. All right? Let's put some hydrogens there. Okay? And hydrogens here. So that you can know that these carbons, the 2nd, the 3rd, the 4th, are chiral centers. Okay? Now, if you have a mirror here, what will appear on the mirror is this Okay? On the second carbon, it's at the left side, or right, sorry. Then it would now on the left side. So the H is there. On the third carbon, the OH is at the um, left. Now we put that, where do we put now? Okay, left, we put that here. And the hydrogen now is at the left side. Okay, on the fourth carbon, the OH now is here. The hydrogen is at the other side. Okay, although there's OH here, but remember, this is not a chiral center. Okay, let's put X, not chiral or achiral. So, um, before we can designate D or L, we know that these are pair of enantiomers. They are mirror images, but we still don't know which one is D, which one is L. But in the previous statement, in the previous slide, I said that what we need to do is identify or locate the highest numbered chiral center. Okay? So second carbon is chiral. Yes, let's put check. The third carbon is chiral. Let's put check. Okay, and the fourth carbon is what? The fourth carbon is chiral center also. Yes. Okay? Now, the condition, as I said, to determine whether the molecule is D or L, you locate the highest numbered chiral carbon. In other words, the chiral center that is farthest from our functional group. Remember, this is our functional group, our aldehyde. Obviously, this is the chiral center farthest from the functional group. Okay, in this molecule, this is our aldehyde. Which one is the farthest? Okay, this one also, the fourth carbon. Now, in this molecule here, in the left side, the OH on the chiral center in the carbon number 4 is at the right side. Then the designation of this enantiomer is D. Okay? Again, the OH or the hydroxyl group at the chiral center farthest from the aldehyde is at the right side. That's why it's designated as D. Okay? While here, the mirror image is what? The OH is at the left side of the carbon that is farthest from the aldehyde. Okay, at the left side, then the designation of this is L. Okay? So you just have to take note to locate the highest numbered chiral center. Although there are OH here at the right, don't be confused that this is a D. No. Okay? Our reference point is the highest numbered chiral carbon. If the OH is at the right, then the designation is D. If the OH is at the left side, then the designation is L. So the D and L are what? Pair of enantiomers. They are enantiomers, okay? They are mirror images to each other. Okay? The D and L, the D stands for dextrorotatory. Okay? The D dextrorotatory compounds are chiral. They are chiral compounds that rotate the plane polarized light clockwise direction. The reason why they have given the designation of D, or in the D stands for dextrorotatory because these molecules, they rotate the plane polarized light to the right direction, clockwise direction. Okay? D, clockwise. Okay? So, the reason why this molecule, the D-glucose, is designated as D-glucose because this molecule rotates the plane polarized light clockwise to the right. Okay? Clockwise or to the right. Now, this molecule, the mirror image, which is an L, the reason why this is designated as L molecule or L-glucose because this molecule, what? Rotates the plane polarized light counterclockwise direction, or it rotates the plane polarized light to the left. Okay? So, a polarimeter, this is a polarimeter. This is the schematic diagram of a polarimeter. Okay? This detects the direction or the optical activity. Polarimeter determines the optical activity of the molecule. So this is the schematic diagram. There's a light source, and then the unpolarized light will pass through a polarizer. Okay, and when a sample is placed on the compartment, okay, if the light bends, okay, to the right or clockwise, we say clockwise, then the molecule is designated as D, dextrorotatory, rotation to the right. And when the when molecule is placed here and the angle of the right the angle of the light rotates counterclockwise, then this is designated, the molecule is designated as L, or levorotatory, left or counterclockwise rotation. Now, between the two, the D and L, the D monosaccharides predominate in nature. They are the most abundant form in nature. However, there are also L monosaccharides that exist in nature, but there are very few of them. Okay? So here, an example of enantiomers, the D enantiomer and an L enantiomer. Okay? The glyceraldehyde, they are mirror images, they are enantiomer because glyceraldehyde has a chiral center. When this molecule is placed on the polarimeter, the light rotates clockwise. This is designated, that's why this is designated as D glyceraldehyde.